This is going to be another statics video, and in this video I'm going to be going over how to approach a problem dealing with the moment of a force about a specified axis. To start off, we have two approaches we can use to find the moment about an axis. The first approach is going to be the scalar analysis. And the equation for this is going to be the following. With this method, to find the moment about a specific axis, we're going to call that A in this case. So to find the moment about a specific axis A, we will simply multiply the force by the moment arm, with the moment arm that we're calling dA being the perpendicular distance from our specified axis A to the line of action of the force. The resulting answer will give you a scalar value that represents the moment component along the specified axis A due to the force F. So the other approach we can take is the vector analysis approach. This method is easier to work with, especially when dealing with a 3D coordinate system. So we know in general that the cross product R cross F will give us a moment as a vector and the I, J, and K hat components. But if we wanted, for instance, the moment component about the y-axis, we would simply use the concepts that the book goes over in chapter 2. So I'm going to write that equation down here below. So if we want the moment along the y direct axis, we would simply write J dotted with R cross F, where J in this case is the unit vector for the y-axis. This same approach, talking about the vector analysis approach, can be generalized for any unit vector. So say if we had an axis, let's call it A again, we would simply write out, let's write this in a different color. We would write out M in the A axis direction is equal to the unit vector of that axis A dotted with R crossed with F. So the name for this is the scalar triple product. So writing this in determinant form, we get the following. Also note that the sign of the scalar value indicates the direction of rotation. So if for our final answer we obtain a positive scalar value, that means using our right hand rule, our thumb would point towards the positive A axis. And similarly, a negative scalar value means our thumb will point towards the negative A axis. So what I'm going to do now is I'm going to go through example 4-57 in the statics book by Hibbler using the vector analysis approach. Let me go ahead and bring our question in here. Okay, so the question is, determine the moment of the force F about an axis extending between A and C. Express the result as a Cartesian vector. To start off this problem, let us write the equation for a moment about a specified axis. So I'm going to change colors again. So in this case, we're going to want the moment about AC. So our equation is going to be moment along AC. It's going to equal the unit vector along AC dotted with R cross F. And in this case, our R is going to connect our force to our axis that we have in mind. So since our axis is AC here, and our force is acting down at B here, we need a vector that will connect the force to our axis in mind. And that we can say is going to be CB right here. this can be our R. So if I rewrite this one more time, we're going to call that R from C to B crossed with F. Okay, so from here we need to find the unit vector AC. So to get the regular vector AC, we know that's going to be the ordered pair at C minus the point at A. And that right there, so the ordered pair at C is going to be 4 in the X, 3 in the Y, 0 in the J, minus at A, since A is the origin, it's going to be 0, 0, 0. So then AC, the vector, will equal 4 in the I, 3 in the J, and 0 in the K. Now from here, we know the unit vector is the vector AC divided by the magnitude of that vector AC. So if we found the magnitude of AC, that would be the square root, 4 squared plus 3 squared plus 0 squared, which is going to equal square root 25, which would equal 5. And then now we can just simply put that in our equation down here to get UAC. So AC we know is 4 plus 3, 0, all divided by 5. So that means our unit vector will be 4/5 I plus 3/5 J plus 0 in the K. Okay. Now from here, we need to find our vector RCB. So similarly, RCB is going to be from point B minus from point C, since we're going from C to B. And B, the ordered pair there, is going to be 4, 3, -2 from our diagram to the left here. And C is going to be 4, 3, 0. So that means our resultant RCB vector will be 0 in the I plus 0 in the J minus 2 in the K. Okay? So now we have our RCB and our UAC. Now with that, we can simply just set up our determinant here. So I'm going to change the color one more time. So let me write out our moment in determinant form. So the moment AC this column right here, this element right here, we know is going to be U, A, C, and the X component, which we found to be 4/5. Likewise, this one is 3/5. Likewise, this one is 0. And then this row here will be our R vector, which would be 0 in the I, 0 in the J, minus 2 in the K. And then our final row down here will be the force. So we have 4 in the I, 12 in the J, minus 3 in the K. Now from here, we're just going to do a determinant, solving this determinant. So let's change the color one more time. Okay, so our first entry is going to be 4/5 times, so let's cross these out, 0 times -3 minus -2 times 12. Okay. Then our second entry is going to be minus 3/5. Let's cross this out. 0 times -3 minus -2 times 4. Then our last entry is going to be plus 0. And since 0 is going to be multiplied with this product, I'm just going to go ahead and say that this is going to be 0 since we don't have to solve it. So now solving this out, I get MAC is equal to, this is going to be 0. This is 0 here. So we have 4/5 times 24, -2 times 12 times the -1 is 24. And then we're over here, we're going to have 3/5 times -1 times the -2 times a 4 is going to be 8. So then if we evaluate that, we'll get a scalar value of MAC that is 14.4. The units here are lb foot. Okay, so this is our scalar value of MAC, but we're not done yet because the question asks for the Cartesian components. I'm sorry, the Cartesian vector of MAC. So what we have to do now, in order to get the components of MAC, we need to multiply MAC by the unit vector AC, since the unit vector represents the direction of our axis. So to do that, we just simply, MAC as a vector will equal MAC, the scalar, times UAC as a vector. So that will give us 14.4, and our UAC from before is 4/5 I plus 3/5 in the J plus 0 in the K. And then if we evaluate that, we go ahead and get MAC as a vector is equal to 11.52 I plus 8.64 J, and again, this is in pound-feet. That right here is your final answer.